Hello, sorry, I'm just getting everything set up real quick because my mic was not wanting to show up, which is... I was worried. I was like, it's done, it's dead. I don't know why it would be dead, it wouldn't make any sense, but, you know... He keeps me on my toes, my mic. I feel like I should explain the mouse airplane, but I feel like it's gonna become very apparent when... Oh. Well, not there. One sec. Okay, so... mouse airplane. Mouse airplane. I have to do fuselage design, but I thought... And I was thinking, okay, like, maybe I could do some, like, kind of, like, fun, like, airplane thing where... Yeah, maybe it's, like, for, maybe it's not, like, for a passenger plane. You know, maybe it's for, fancy people or something. And then I can kind of, like, try and make it fancier. But then I was thinking, okay, but what if... What if it was mice instead of people? It says the weight of the interior components of passengers. The passengers don't have to be people. They can be mice. Hey, how's it going? The stream is pausing? I hope it's not pausing. My bitrate might be shit. Maybe. I don't know. I can't tell. It seems maybe okay. It says I haven't dropped any frames. But yes, we're doing mices. We're doing mices today. Let's go. I'm so excited. I need a formula for how many mice I can fit in this plane, guys. It's gonna be awesome. I want to see if we can design like $100 mouse fuselage. Mice plane. Yeah. We do have to start with like the basic stuff. Which is, you know. So it's just it's basically just a cylinder. It's a cylinder and then we're gonna put some stresses on it. We're doing thin-walled, so essentially we have to say, there's the one thing we care, here's our mice airplane. It looks like a big can. The printer people haven't gotten back yet? Wait, that's kind of crazy. That's a long time. Our assumption for it is a thin-walled pressure vessel. The thickness has to be less than 1/10 the internal radius, I want to say? What is it? I think it's the internal radius. Let me see. Let me check. I wonder if we can make this out of some kind of pre-existing can. That would be kind of fun. Like an airplane fuselage out of, like, you know, maybe we can make it out of, like, there's probably nothing thin enough that you could get. I mean, I could just search for, like, industrial tin can, essentially. It's so cute. I want to make, like a Snoopy plane. Okay, we need to start with the basics. Our thickness, where is it? 1/10? Yeah, 1/10 Ri. So that's our first thing. So the question is, we need to figure out what this is. This is the first question mark. And this depends on the number of mice we want to fit in this plane. I don't know what to do now if they won't respond. You could try calling them. Oh wait, okay, loading conditions. Alright, the atmospheric pressures won't change. But I feel like starting with how many mice we can fit in the plane is kind of like a good start. So how big is a mouse? How big is a mouse? Average mouse size. See, okay, when you have a regular airplane, is it as tall as it is wide? Okay, house mouse has a small, slender body, 6 to 11 cm, 2.4 to 4.3 inches long. Let's say it's 4 inches nominal. Okay, 4-inch nominal mouse size. But that's like long. That's okay. I guess it has to be. Okay. 4. I'm gonna draw the mouse. Here's our mouse. It's a very scientific drawing. He's got bunny legs. and little feet. There we go, that's a mouse chat. What do we think? Wi-Fi is fine, Twitch is being weird, I gotta go. Oh, bye! Okay, 4 inches nominal. How wide is a mouse? I wanna know how wide it is. Is nobody telling me how wide the mouse is? Is it like 1 inch wide? What do we think? Average mouse width. There's no way. Probably about 1 inch wide on average. Okay, I was kinda cooking there. This is so funny to me. This doesn't even, okay, width. Wait, what? Ounces? Oh, wait, I didn't read that. I was like, what the fuck? Okay. Yeah, this is not, okay, height. Whatever. That's not the width. Well, I mean, if we assume them to be a circle, a cylinder, then I guess it's close. Let's say like 1.5. We'll say 1.5. So that's the one we care about. So 1.5 inches. Now, how many, if a mouse is gonna have a chair, we're gonna say the mouse chair is 1.5 inches. Just this for simplicity's sake. We're gonna say this is 1.5 inches. Now I guess we should make it like 1.75 inches. Mouse chair. Very important diagram. Okay. There's the mouse chair. So now, how much space are we gonna have in between each mouse chair? I feel like if that's 1.75, I mean, they can just like basically have no space. We'll just say that. There's no space in between the mouse chairs. Because there's a little bit of space, like, if our nominal mouse is 1.5 inches, then, you know, they have some space. So I think that should be okay. So they're right there. I feel like, and then we can just say like like the aisle is 1.75. Oh, we could do like a 3-aisle mouse plane. Wait, this is awesome. Okay. No, we're gonna start off small. I think we look at, okay, so R for, okay, so this is the two seat, 1 aisle. 2 seat, 1 aisle. There's a 3 seat, 1 aisle. These are just like, you know, regular plain things. And then we could have like, 3 seats, 2 aisles, which would be 9 mouse radius. I feel like this is a good like setup. Let's say 3 seat, 3 aisle. You know, and if you wanted to use this for some other kind of animal, like a human, you know, it wouldn't be that much different, but, you know. We're asking the real questions here today. Okay, cool. So we have some of our things. I am gonna set this up in MATLAB, I think. In RATLAB. Imagine if I like had like a mod for MATLAB to like change it to like RATLAB on the starting screen and then like it changed all the little things. Sorry. I'm like way too excited about this. I'm so happy, guys. I'm so happy that I get to design a mouse airplane. And it's like they asked me to design a mouse airplane. I mean, they didn't ask me to design a mouse airplane, but they allowed me to design a mouse airplane. And that is truly the... I feel like my professor isn't ready to handle this. This is my other calculations, and then if you look, if we scroll down, you see mouse airplane. Mice mathics. Exactly. Okay, so let's make, I guess I can make a function. I'll set up this first. So R, and then we can do like a loop or something over the different R's. But no, we'll do this first. So we want to find, this is going to be the R inner, or we'll just call it like 2, 1. So like 2 seats, 1 aisle. And that'll be Wait, wait, wait. Wait, I can just do... I'm trying to think. Would it be better if I just... Because it's going to be the same thing. So R inner equals... Because I want to just maybe say seats. Seats, aisles. We'll say 2. So then Ri equals aisles plus seats times 1.75. And this is in... Oh wait, aisles times 1.75. This is in... Oops, in inches. Okay. I think it's actually kind of nice that it's in inches, because like PSI is in inches, so we don't have to like do anything really. That's R inner, so we need R outer is going to equal R inner plus thickness, and we'll have to set the thickness to something. We might want to solve for the thickness, so I'm gonna actually leave it out. I lied. We need some pressures now, I think. I'm gonna change this so that it's just, these are just our different setups. We don't need this much space for that, because we're not gonna be doing the analysis 3 times out. We'll just have it in, oh, sorry, I need to switch my thing. There we go. So those are our 3 setups, just to kind of, you know, let people know. And this is, right now, this is not about the length at all. This is only about the hoop stress. So we'll start with the hoop stress, and then we'll go from there. Okay, so mouse airplane. I guess it would... Does it reach the same altitude as a human airplane? Or should we like find the altitude the human airplane goes to and then scale it by like the height of a human? No, but it's like so you can ride the jet stream, so it should be up that high. This thing is gonna be like... It's not gonna be crushed, okay? Steel doesn't like change being steel. In my mind, it's like, okay, it's small, so it should get crushed easier. But that's not really how that works. Okay. Let's see if we can do this. I need a adiabatic model for atmosphere. Yes, adiabatic lapse rate. P over Py. I kind of wish I could just... I mean, I could just do rho gz and then find a density for the air, an average density for the air. That might be kind of easier. Rho g, but our z is gonna be negative. Chat, I don't know, chat. I feel like adiabatic lapse rate is gonna be the way we go. No, but then I have to actually do a differential equation. Can I get a calculator for the pressure? Come on. Wait a second. Like, my hand out. Where is it? I think there's an air pressures at different heights in this. I think there is. Atmospheric pressures at different altitudes. I hope it goes up high enough. Wait a second. Wait. We're cooking. That's moments of inertia. Okay, fluid properties. No. Common liquids. No. Where's my air stuff? Fluid properties. Water. No. Gases. Closer. There's like a table of like only air stuff. Yes. Okay. Altitude pressure. Oh, let's go. Okay. So what is the altitude an airplane normally goes to? I guess we're gonna say assume. So these are our like configurations. And then like assumptions. Mouse airplane goes to same height as human airplane. Travels at same altitude as human airplane. Okay, that's one of our assumptions. So we need to find the pressure. So pressure at where what altitude is cruising? Wait, okay. As it goes higher, is it more? Wait, let me, I can see. No. Wait, the pressure is like more on Earth. Wait, that's fine. We just design for the atmospheric pressure. I don't know how to change internal cabin pressure. I'm gonna be real. Wait, oh, internal cabin pressure will be... Because we want to keep it 1 ATM inside, and so the difference, is 0 at the bottom, and then... Okay. So we'll just look at the, like, cases here. So ground. And this, again, is for, like, the hoop stress. So you have, like, PATM in here. And PATM on the outside, so we're not really worried about that. But then, like, cruising, which is, I think, as high as you go, right? 30, uh-oh. Okay, we can just say, like, around 40,000 feet. Around. This says 3,800 feet. But let's just round because my table says 40. Alright, pressure. So we still have the inside pressure as PATM. Because otherwise you would get crushed, right? It has to stay the same. I don't know how you keep that, though. Oh, I guess you just pressurize the cabin. Never mind. Okay, yeah, it's not like leaking air out. That would be also bad. Okay, the pressure is 2.871 times, so 2.871 times 10 of Newton per meter squared. That's not great. We're gonna want to convert that to Newton per meters to... What are we in for PATM? I guess it might not matter. It kind of matters. PSI. PSI is what I want. Newton per meter squared to PSI. Divide the result by... Whoa. For an approximate result. 6894 let's say 6894.75. Divided by 6894.75. This is okay, I was about to say this is like an approximation. I think that the thing that I struggle with in terms of like the design side of this is I don't really know when you can approximate certain things. Like, is it an issue that I'm saying 40,000? Because if I was, like, I don't know, evil mode? Well, never mind. I'm gonna approximate everything because I'm evil now. So thanks for answering that question for me, chat. I'm not worried about this at all. This is a normal thing for me. Okay, let's see how much pressure we have in this 2.871 times 10 to the squared divided by 6894.75. Ooh, that is small. That is tiny. What the heck? It's so small, just like the mouse is. How much is a PSI? If 1 ATM is like 14 PSI, something like that? 14.5 or something? 1 ATM to PSI. Yeah, 14.69. Nice. Sorry. 696. Okay. Alright, we have our pressures. Now we get to do our engineering approximation is pure evil to math nerds. Okay, no, but like error, you know what I mean? Like percent error. Like, first off, if I design the pressure, if I'm saying like, oh, we go up higher, that means that there's a larger pressure differential, which means it's safer because I'm choosing a number that's bigger than the number that I need to. Yeah? See, but like I don't know like if I'm just supposed to do that. If I'm supposed to design exactly like a lot of the time in engineering, it's like okay, well we find the exact amount where it's gonna like just squeeze by, and then we just multiply that by like 4 or 5 or something because you have a safety factor. But I don't know. He didn't specify any safety factors. I don't know what it is for airplanes. I guess I could look it up. I want these mice to be safe. I don't want these mice to be not safe. This is scary. Okay. EATM equals like 14.696 psi. We'll say that. Okay, so now we have to look at hoop stress and other stress. That is for a changing thing. This is for, here we go. So now we're looking for the thickness. That's what we're doing right now. We're trying to find the thickness. So thickness equals what? Because we've got our length, or our radius is determined by the mice we're getting in there, and then wait, let's see. What are the loading conditions? Sure, I did that. What are the important dimensions for your fuselage? How would they affect the assumptions for your analysis? Wait, what? Nominal dimensions now, and then adjust them based on future results. Well, yeah, I mean, we can do that. Calculate the average and maximum tangential stretches. Yeah. Yeah. Oh, okay. I really like this mouse. This is a good mouse. We're gonna keep this guy safe, chat. Okay. So, our pressure. The one thing I don't know is... Oh, wait a second. No. We need external pressure vessels, so we need these other equations that I didn't write down because he said don't write these down. Yeah, P out is not that much bigger than P in. Well, no, I say we just do this and we get it. Because, I mean, it's not really going to be that much worse. We're just doing it in MATLAB, so making this mouse as safe as possible. All right, where are we going? We're going to look at the it's not an internal pressure vessel. It's just a pressure vessel. Wait, did he say internal? I think he said thin-walled pressure vessel. Yeah, okay. Okay, good. We're learning. Modules. I need pressure vessels. Where is that? That is 7. This is so fun. There was one question he asked in class, which was like, you guys know the what's it called? Pillsbury dough, like cinnamon rolls and stuff. How you kind of like crack the thing open by like smushing on it. He was like asking us how we would design that, and I was like, oh, this is so cool. Okay, here we go. These are our stresses. Now, sigma, okay, yeah, sigma L will be the same. Okay, cool. This is it's chonky, but we're gonna use these. So, this is gonna be where our MATLAB comes in, because we're also gonna get... Oh, wait. Wait a second. Oh yeah, because we'll figure out the well, we have to pick our material. All of this is to find the thickness, but we need to pick our material, so I don't know what normally we would do. We want to use not composite, we want to use metal or something, because we don't want it to deform. I learned that from... What was that one called? Ocean Gate? Or the submarine, the submersible that crushed everybody inside it to death? Anyway, what are airplane fuselages made of? Probably aluminum and carbon fiber. Oh. No, it is composite. Carbon fiber. Do we do carbon fiber mouse airplane? Or aluminum. I feel like we should do aluminum because I feel like mice maybe don't have carbon fiber as accessible to them. Maybe they have it more accessible because they can like weave it themselves with their tiny mouse hands. I mean, their hands aren't that small. I don't think they could do that. But carbon fiber is a synthetic material. I kind of want to design a very, very small mouse airplane. You know, one of those like two or three person, I guess 2 or 4 person airplanes. That'd be so cool. Anyway, oh my god, are airplanes made of aluminum or titanium? They are not made of titanium. Wait, which aluminum is used for airplanes? 2024. Okay, we're gonna say aluminum alloy 2024. So, material. Aluminum alloy 2024. All right. And then we're gonna look up. One of my swim team kids way back when was scheming to make a mouse house. Aluminum alloy 2024. That's awesome. Properties. Like a harness. Oh, a harness for a mouse to become a computer mouse? Wait, that would be such like a good little funny YouTube video. I feel like that would be easy. You could do that. What the hell is this? This is like a... Okay, well... Ultimate tensile strength, tensile yield strength. I guess we probably want the tensile yield strength. That's gonna be 324 megapascals. Tensile is that a sigma? I just want to make sure that's not... I think so. Equals 324. So we're gonna design this right at the edge, and then we're gonna pull it back. So sigma, which one of these is gonna be larger? T or R? Let me just check for an internal pressure vessel. I think sigma... Wait, what? Wait. Whoa. Oh, okay. We don't really know. Poor mouse would just need to be sure he didn't wind up with a gamer. Oh, you know, I wasn't even thinking about that. I was thinking, like, the mouse would just be controlling the computer with its movements. So we're just gonna solve... Oh boy, this is gonna be kind of annoying. Oh no, it's okay. It's okay, we need to do a little bit of algebra. Oh, and by a little bit, I mean a lot of algebra. Okay, it's fine, it's fine. It's fine. I wonder if I can put this in a solver. You think Wolfram, if I gave it this and said, like, solve for t, it can do that? I think so. Algebra's not fine, it's scary. If I do... I'm just trying to think. I think if I graph this in Desmos, it can give me the answers. But let me think about that. Because, okay, Ri... I guess, do we want to say, okay, we found our internal. Ri is given. Given by conditions. So R outer equals Ri plus T. And then the pressure here is that's just gonna be our pressures that we have. Okay, I just need to see if we can do this in this. So, I don't know, chat. I feel like we are not gonna be able to do this in this. I feel like this is gonna be a little scoffed. Okay, R outer. No, we can't do R outer. I keep typing R outer and I want it to be R outer, but it's not. Okay. Like, if I say, like, 365 equals something, 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 it's not gonna solve that for me. So, I think we might need to Desmos. Let me do this. Sometimes not everything can be done. Wait, can I, let's see. Use MATLAB as a solver. Oh. You just put solve. Oh my god, you can. What? Oh, okay, you can just do that. Wait, that's crazy. Okay. So, I just have to define an equation. Okay. So we put in our, let's put in our equation then. Wait, I'm gonna put this over here so I can see it really big. And with MATLAB, all things are possible. Well, maybe not all things, but some things for sure are possible. Okay, pi ri squared minus po ro squared minus ri squared ro squared po minus pi. Oh, you know, just casually. And then all this divided by, you know, yeah. Oh, I also messed stuff up. Pi times ri squared. Whole row. There we go. And then divided by r squared times ro squared minus ri squared. Okay. And this is gonna equal, what did we have? We said 3. Could you use SYMS? I've never solved anything in MATLAB. Well, I've never like solved something non-explicitly, I guess I should say. So there's my equation. I need to set up my pi equals, p inner is 1 ATM, so that's the 14.696. That's in PSI. And then p outer equals, I'm a little worried, no, because MPA, oh wait, that's in MPA. I need that in MPSI, I think. Yeah. PA to PSI. Divide by, okay, 6895. That's what we did before. So, and then P outer is what we had before. 0.042 PSI. Now this can be a little bit more similar to that one. Okay. So that's that. And then RO. I mean, I guess we could just solve for RO. We don't need to solve for T, because then we can just get RO and then subtract it. So then, I guess this is just saying... Where'd it go? Where'd it go? Wait, what the? What the? Hello? Oh, I opened it in Firefox. Solve equation. Oh wait, yeah, it's SMS. SYMS, you're so right. That's what you meant by that. A, B, C, X. So what do I need to do? Do I have to just define all of the variables? Do I have to say PI, RI, PO, RO? I don't know. And then S equals solve equation for RO? Oh my god! Holy... I don't like that! Oh boy! Can I have it formatted as numbers, please? Can I also, like, put the values in there? Oh god. We're learning. We're learning. This mouse is gonna be so safe. You don't even understand. Can I take that and then can I use that? Like, it's not picking up. Okay, what if I got rid of this? Then would it just fail? Oh no, there we go. Wait, why is it I though? Can I make it real? Why is it I? It shouldn't be I don't think. Why is it not giving me real? Real equals true. What if I just did that? Real equals true. Maybe you can do VPA on it or simplify. Maybe it's supposed to be negative. Nope. Maybe I typed it in wrong. Let me look at it again. Sorry, bring this over here. Pi times Ri squared minus PO RO squared minus Ri squared RO squared times PO minus PI over... Yeah, that all looks fine. And I don't think these pressures should be negative. What is VPA? You know more than me. MATLAB VPA. Variable precision arithmetic. What the heck is that? Uses... Oh... I'm gonna try simplify. That looks scary. I just want to solve this. I might just throw it into Wolfram. Wolfram can probably solve it. Simplify. Oh. Oh. Let me see what simplify looks like. It's gonna be like the same thing. Oh? So, why does it do that? My question. Wait, but then what if I solve this? Wait a second, wait a second. Let's call this simp. And then we say S equals solve simp RO. God damn it, it's still I. Why? Why? Let's try Wolfram Alpha. Equation solver. Maybe. I don't know. This might not work. VPA var precision. Oh god. Can I not delete that? What the heck? Oh. Okay. Let me try this instead. Wait, what if I just try to copy and paste it? It can probably pick it up, right? It's smart. Oh, it actually kind of did. What was it, 3? It's so tiny. 324 times 10 to the 6th. Okay, I believe. Solve. Go, go, my Wolfram Alpha. Wait, I didn't put any of the... I didn't put any of the values in. Uh-oh. Wait, what? Oh, I see. Interpreting is 320... I don't want to do that. It just told me 324 times 10 to the 6th. Wait a second, we gotta go over here, chat. Come with me to a beautiful world of... Oh, my Firefox doesn't exist, apparently. Well, you can't come with me. Why the heck is it so hard to solve one equation? Okay, let me just try and switch it to... I'll just put all in stuff by hand, and then we'll solve it. I just don't understand why it's... The inner is that. A really useful command is latex. Is that just like, wait. Let me see. And find their latex forms. You just can copy paste the solution into a paper. Yeah. I know latex. I just didn't know if it's... Is it just a... I just want to solve my... I just want to solve my thing, man. Man, now I gotta like... Okay, wait a second. Let me pull out RI real quick. 5.25. E outer we have. That's... I'll do that one after. P outer... Oh, maybe it's assuming that P outer is larger than P inner? Or maybe not. I don't know. I don't want it to do that. That might be why we're getting I. Just a guess. R outer. I'll change that to just R. Then R squared. What the? What is R squared? What? Wait, what? R squared? Is it like a nominal? Huh? Oh, where we are in it. Ooh. We want that to be R outer has the largest, I think? Yeah, that makes sense. Okay. R squared, that would be, oh, that would just be RO, okay. And then R inner is 5.25. And then P outer is 0.042. Okay, if it gives me 324 times 10 to the 6th, then I'm going to be sad. Well, can it solve this? It can solve for RO. I don't know if it... God, it doesn't... what? Hello? Oh. Solve for R. Wait, we might be getting somewhere. Chat. What? Wait, what if I just do this? I'm sorry, this is... Why am I not just bro? Wait a second. How's it going? Hi. Let me get this over here. We can't not be looking at this. I'm gonna put it into Desmos instead because all my homies love Desmos and I don't want to deal with anything else. Where are we? There we go. Okay. I've changed stuff slightly again, just into X. Come with me and you'll be in a world of pure imagination. Okay, X. Where are you? Can I see it? Where'd it go? Where'd it go? Is it really large? Uh-oh. Can I graph it is the thing. What? Is it because I put an equals? Oh. What is this? Oh. Okay, this makes more sense. As it gets really small, as X gets really small, then it gets, like, the stress goes exponentially up, and then as x gets smaller than the other one, stress goes exponentially up in the other way. And then as we get here, then... Wait, but where can I find... Oh, okay, so I just need to, like, figure out... What did I... Okay, I don't know what I did. But I need to find where it's... Wait a second. Y equals... Oh no, 324 times 10 to the 6th. It was really big. It was. Where is it? Where is it? Oh my god, it's huge. There we go. Is it even gonna cross there? Does it get there? Uh-oh, chat. I don't even know if I can get it to cross there. I think it starts going down when we get to... I mean, it, like, should, but what if I, like, just... Can I, like, intersect these? Wait. Oh, shoot. Intersect on Desmos. Point of intersection. So that's not helpful. What if... No, I don't know. Yeah, no. So what we can do... That's 5 inches? We definitely don't want 5 inches. We want, like... Let me think. R outer... Oh, wait, no. R outer minus R inner gives us our thickness. Okay. We can just figure it out. The stress. Okay. So max RT, okay, T equals R outer minus R inner. So R inner is the 5.25. So 5.25 minus... Isn't there a vertical asymptote? There is, which makes sense. But... Wait, where's the vertical asymptote at? I guess the vertical asymptote should be at x equals 5.25. Yeah. But I want it to... Oh, I see how it is. Okay. Wait, oh no, don't look at that. Look at this. So, let's just say that, okay, what if we have the stress be like... The thing is, like, this is not a lot of stress. This is 700 compared to this much. That's the stress that it fails at. And we're considerably lower. I want to just check. It fails at... Oh, wait, pascals, PSI. Wait, shoot. Oh, it's slightly different. It's slightly different. Oh, shoot. Okay. Megapascals divided by... Okay. So it's slightly different. Chat, we almost made this mouse less safe. To be fair, this is going to be like 4 million times safer than it needs to be. But still. Okay, this divided by 6894.45. Okay, so it's 46,992. That's considerably less. Okay. Yeah, but still. So let's say safety factor. Oops, here, I'll pop over here. Let's just say that. Wait, what is the safety factor for airplanes? We can look it up. The ultimate factor of safety, 1.5. Let's do 2. Let's do 2. It's gonna be a lot less than 2 because, I mean, well, I guess if our... whatever, we'll figure it out. Equals 2. So, whatever this is divided by 2 is 23. 23 or 96. I'm getting lost in the sauce, but I'm excited. I'm having a good time right now, so. Alright, that's our that. I feel like there's a better way I can solve this, though. Should I didn't even try doing the algebra at all. I feel like I should maybe try doing the algebra. So let's just say this. Let's say sigma t is 2, 3, 4, 9, 6 psi equals. This is a constant. PI, we know that. Minus, that's C1, minus C2 times R I plus T squared minus R minus a constant times Ri plus T squared. We can at least solve for this, Ri plus T. Like, that's not really that big of a deal. What are we looking for? Okay, we're designing a mouse for everyone who's just coming. We're designing a mouse airplane. And we're trying to figure out the thickness right now. That's what we're doing. I'm gonna just call this. Wait a second. Yeah, what if I just solve for RO? It sounds stupid. Okay, RO squared minus another thing, RO squared. R is where we are, which is gonna be RO. Divided by RO. Wait a second. Wait a second. Sounds absolutely genius. Yeah, like rat boy genius. Well, this is for mice, not rats. Actually, big difference, because mice are a lot smaller. The nominal size of a mouse is probably at least 2 times as small as a normal size of a rat. This just cancels out. Right? And then we just have RO squared minus constant? What was I doing? Why was I doing all this garbage? We could... Chat, I'm sad. Okay, let me do this properly. I'm sad, chat. Alright, PI RI squared equals C1. R equals R outer. That's the maximum stress place. The maximum stress place for the tangential, I want to say? Yeah. But the inner is the maximum one for the radial. You know. Classic stress. Okay, so... then PORO squared. What if... okay, wait a second. So 2, 3, 4, 9, 6 equals minus PORO squared minus RI squared RO squared PO minus PI divided by RO squared. This, and this. Oh. Okay, it's like... it's a little more janky. Yeah, because this doesn't have an RO in it. Man. Okay, well... it's not that I can't graph it, it's just... I want to solve it. I don't know why putting it in the solver, like, gives me I, though. It shouldn't give me I. It should give me correct values only. Yeah, because if I do this, then... How do I even... I can't cross that out. Ugh. That's kind of nasty, not gonna lie. Because I've got these ROs on the bottom. Can I even algebra this out? I don't know if I can, chat. Maybe, wait a second, maybe... I had all these R's in here. These should be ROs. In my MATLAB. Oh, I just had one. Let me try it again. Oh, dear God. Well, I got rid of the I's. That's the wrong thing. I mean, it's kind of the right thing, but it's like also not. I got rid of the I's, but now I got this. Wait, what is the simp doing? Why is it doing that? I don't want to do that. Just put it into this instead. Do it with equation, not simp. Simp is bad right now. God, why is it doing that? I want to solve it for RO. Oh wait, only real, only real. Wait a second, wait a second. Wait. Okay, but how do I get it to calculate it out? That's right, that's right. Wait, that's right though. Okay, but now like give me the number. How to do that? How to do that? How to do that? Get number. It's okay. We're just taking. Okay, here's what we did. Let me explain. It's actually not that hard. So basically, we said this. We said, all right, we want to fit a certain amount of mice in this plane. Right. So these are the different seat configurations that we're going to test out. So we have like 2 seats and 1 aisle. So that would be like 4 mice across. If you have 3 seats, 1 aisle, 6 mice across, and then 3 seats, 2 aisles, then that would be 9 mice across. Right, so those are different ones. And that gives us the radius of this. So basically we're modeling this as a big cylinder. We're not trying to put any curvature into it or anything that's fancy. So we basically have this cylinder, and we're saying, okay, so the cylinder has really thin walls. And so we can model it as something called a cylindrical pressure vessel. So we need to know the pressures on the inside and the outside. So inside the cabin, when we're on the ground, is going to be 1 atmosphere, and outside it's going to be pushing on it with the 1 atmosphere, right? Because we're just kind of outside. Then as we get up into the air, the pressure is significantly smaller because the air is like thinner as we go up into the atmosphere. So now we have a pressure differential. VPA can be used for getting decimal. Okay, thank you. I was about to Google that. So we have a pressure differential, and that's going to cause stress because the inside of our thing is pushing out. It wants to rupture. It wants to blow up the airplane. So then we choose our material, and this I just looked up like, okay, what are airplane fuselages made of, like the airplane cabin? And so that's just this specific alloy. And then we say, okay, so we have a yield stress, which is like, this is where if our pressure causes this number, then our airplane blows up and our mouse are dead. So we don't want that. And what we're essentially saying is, here's our safety factor, which is like, how many more times are we going to make this? How many times safer are we going to make this? So if this is our number where everybody blows up and they're dead, we don't even want to get close to this number. We're only going to say that our maximum is half that number. So you shouldn't ever get close to that number. And then what we can say is, okay, so we know that this is a cylindrical pressure vessel. We've modeled it like that. And we have these equations for getting this kind of number out of this shape, essentially, with this pressure. And so that's what we're doing here, is we're solving this equation to figure out how thick this should be so that we don't get to this number. And the thicker we make it, the farther away from this number we get. But we want to make sure we don't make it too thick, because then it's like we add extra weight and we waste material. So that's basically the process of that. Kind of like taking all of our stuff and then like backing out things. Okay, might just be able to do double. I did format like that. I don't know if, wait, let's see. Solve equations. Solve equation on MATLAB, get out double. Sim equation 2 double. There are two values for y. Okay, you can use VPA after. Wait, no. Solve. I'm gonna go back to solve. Name value, return conditions true. Can I solve it with... Oh, okay. Yeah, so we use VPA solve after. VPA solve? Oh, VPA solve. So instead of that, instead of solve, we can just use VPA solve. So if I do that... Damn it. Oh, no, not real. Let's go. Okay, 5.2. So, okay. Okay. That's very funny. So what we got one negative, one positive, which is just because it's squared, but that doesn't really make any sense. We can't have a negative length. So RO is going to be 5.25085. So the thickness is 5.25. So RO equals 5.25085, which means that thickness is RO minus RI. And that's 0.00085. Now that is very small. That is 8/10 of a thousandth of an inch. Generally in engineering, we measure stuff in like thou, right? So this is like 8/10 thou. That is a little, I feel like this is very under, oh wait, no, okay, this is not underdone actually. This is when we just had, so right here, if we look at this, we just converted this to PSI. This is not with a safety factor. Well, you just need to know the thickness of the higher pressure because the thick... Yes, exactly. Yeah, so we're choosing our highest pressure, essentially. Right now, this thickness is for the absolute maximum. But we want to make it safer because we don't want it to, like, always be about to fail. So we're gonna divide this by 2. And it's gonna get a little bit bigger, I think. Let's see. Oops. Whoa. Why did that break it? Oh, what the... Wait, what? Multiplying that by 2 broke it? What? Oh, the parentheses broke it. Oh, I see. Wait, what? Doing nothing broke it? Uh-oh, chat. Oh. Oh my god, wait. Doing nothing broke it. Fuck, never mind. What happened? What happened? What did we do? No, we broke it, chat. We broke it. Oh no, how did we break it? Oh god. Go back to a time when it worked. Okay, wait, if I go to solve, no, wait a second. If I go to solve. What? Wait, solve also broke it? Wait, what the fuck? Why does it say equation logical equals 0? What does that mean? Do I put a parenthesis? What? No, chat, what did we do? Okay, what about that? I didn't change anything! Oh my god. Wait, how did that actually happen? Wait, what? I literally didn't change anything. Okay, what if I get rid of this? That's still fucked up? What the hell? What happened? Oh. No, that's fixed. Oh no. No, we had it. We had it. We had it. Oh, no, wait, I think this is... Was it because we did simplify first and it got the values in, then when we solved it? I think we might need simplify. Wait, but it doesn't like it now. What the hell? What if I say equals like that? Nope. Doesn't like that. I don't know what's happening. Maybe it's that your symbolic expression is no longer symbolic. Oh, I did get rid of sim. Maybe it's like S. Yeah. But I only want RO to be symbolic. Can I just do that? Oh, okay, there we go. Strange. You know what? I'll take it. We don't need to. How did I fix this? I changed the VPA. That's what I did. And then get rid of the real. That is very interesting that it was working before. Okay, so I need to divide it. I need to divide it by that number that we had before. Well, what was that number? This is very wrong. Well, okay, yeah, no, it's wrong because it's in the wrong units right now. I was gonna say this is 0.75. Okay, so yeah, this is our absolute minimum. This is our minimum thickness that we can do. Is this, and then if we multiply this by 2, then that's what we want to do. Okay. I guess I can just define a safety factor. San Francisco. There we go. Okay, there we go. That feels a lot better. So let me say RO equals... Can I just say, like, S2? Does that work? No. How do you get values out of S? 2? That's like a function that I'm calling. Oh, no, that worked. Okay. So then T equals RO minus RI. And I want to see what that is. Okay. We don't really need to see that because that's just that. Okay, cool. So in this case, it's going to be 2 thou. That's what we're going to use. Which is pretty thin. I'm just gonna round because, I mean, yeah. Oh my god. Okay. We did it, chat. We did it. Okay, well, we have to check the other one now. So that was our S for... So this is gonna be sigma tau. Yeah. So this is sigma tau simp. No. Oh, we don't need to do this. Oh. I didn't need to simplify it. I think that still works. Yes, we're chilling. So this is... I'll just call it ST. Okay. We're chilling. So now we need to make sigma R, which is slightly different, but not that different. It's gonna be the same failure, but in this case, now we want RO to be RI, because our maximum sigma R is at the middle, at the inner point. So I can't look at that, that's not right. I gotta pull this over here. All right, we're gonna be using this equation now. Oops. Hello, 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 mouse. Mouse doesn't want to work, nice. This equation right there. Man, designing a mouse airplane is not as... Well, I mean, I guess it would have been a little easier if I had known how to do the solver stuff. Yeah, okay. I think the only thing... Wait, what? Wait, why do we not change anything? Oh, there's a plus. This is a plus. instead of a minus. Yeah. Okay, so now we do S. Sorry, let me move this over. Oops. That's my bad. There we go. Just a plus right here instead of a minus, and then we're gonna do sigma R instead. Solve for RO and call this SR, and then we'll call this RO1, and then we'll do T1, RO2. We don't know which one is going to be bigger, so we'll have to pick the bigger one because this is it's our definition. By definition, we want to pick the one that's going to fail. Like if one needs to be bigger, essentially, we'll pick the bigger one. So as we can see, in this case, our thickness 1 is bigger, so that means that our tangential, or like pulling force, is larger than our radial force. So that means that we're gonna need to pick 2 thou. Either way, we could probably have picked 2 thou, so whatever. But we'll. That's so cool. Holy shit. But this is for the first configuration. But now we can see, like, in the other configurations, how much more stress it's gonna have. So that's just our first configuration. Right there. So let's see if that's very small, but you can zoom in on it. If we change it to be 3 seats, how much larger our thickness is gonna have to be. Oh, look at that. We have to go all the way up to, like, probably 2.5 thou. If we want, I mean, you might be able to get 2.2 nominal. Well, I guess it'd have to be 2.3. It could be 2.2. We are doing a larger safety factor than we need to. And then that's like, how many are we increasing by? We're going from 4 to 6, and we have to double the thickness. Well, no, not double the thickness, is that right? This would be about, I said round up to 2 thou. This one, we'd be going to 2.5 thou. And we're not really even doubling that's 4 to 6. Then, okay, if we change the aisles to 2 and we do 3 seats, then let's see what we get. That might be the best, because that's gonna be 3 thou, and we're going from 2 thou for 4 to 9 for 3 thou. That's pretty good. Now we haven't done the, so wait, this is like 0.02. And I guess we should just check that that's less than 10, well, what's our radius? Like 5.25. That for sure is smaller than 10% of 5.25, right? Yeah, for sure, okay. For 4 mice. And then we get this one, which is 9 mice and 3 thou. That's like pretty good, I think. Now, of course, like weight and all that other stuff is a question, but we don't really care about the weight. We just kind of care about the thickness of the material. And then we can just make it, I mean, really, we can kind of make it however long we want to. 9 mice. I'm gonna choose this one. Because that's pretty good. That's pretty good, chat. We're making like a little, like a big ass mice carrier plane here. The only other thing we have to do is length, which we have another equation for. Where is that? Oh, here we go. Oh. Wait, but that's not an internal. Ooh. Shoot. I don't know if I have an equation for a pressure vessel, like, length. Let me see. See that he didn't even give us the length one for this. Shoot. Okay, I guess I can look it up. Let's see. So pressure vessel. So, yeah, the issue is, like, you know, we could have used a thin-walled approximation, but for the thin-walled, the equations that I have are also for only internal pressure vessels, which is A, not what we're doing, and B, yeah, we just can't do that. Okay, pressure vessel, what is it, like longitudinal stress? Yeah. It's gonna give me approximations and I'm gonna cry. Bro, I don't want the approximation. Come on, man. I don't want that. I want, like, pressure difference. Pressure vessels. Oh. Sphere. What? Oh my god, these are all the approximations. Come on, man. This is a paper. I just need the... Come on. Stop! Why are they doing this? This is so messed up. These are all internal. I don't want internal pressure vessels. I want, like, either an... Well, I guess it is kind of an internal pressure vessel. The higher pressure is on the inside. But I just want... Oh. Wait, external pressure only. No, stop that. I want internal and... External and internal pressure. No. Maybe it's in the book. Probably a better place to look. Let me see real quick. What's the name of the book? The book is... They have kind of like a funny, silly name. Let me see. Sorry. Syllabus. Shigley. That's what it is. There we go. I was in my brain. That was in my brain. Far in my brain. Okay, I'm pleased that I haven't spent the entire 2 hours on this. I thought I was kind of gonna end up doing that. Failures from... Where are pressure vessels? Stresses in pressurized cylinders. Here we go. They also don't give me the longitudinal stress. These are only for... Oh, wait a second. No. Nope. God damn it. I want something that is more... Well, that's all I have. I don't have a PO minus PI type beat. You'd think that someone wants to do this. Like, just as a general thing. I would love doing EE while listening to Damie struggle. Actually, okay, it's less struggling than I was before. We can get to the struggling when I do a dynamics problem and it turns out wrong 40 times in a row. I had to ask my professor, I was like, I'm adding these numbers. I did it in MATLAB too, like, so it wasn't just me adding the numbers wrong. I was like, I can't figure out why this is not working. And she's like, oh, because I was like, my acceleration is wrong. And I was like, oh, well, I was doing like v squared over rho. And she started explaining how it's not just v squared over rho. And I was like, I didn't mean that I was just doing v squared over rho. I was doing everything with r double dot being v squared over rho. And I was like, yeah, so I did that. And she was like, wait, so you're getting the wrong answer? And I'm like, yeah, I don't know why. And she's like, well, I don't know why either. Stress analysis of thick-walled cylinder. Wait a second. We might be chilling. What if I say thick pressure vessel? That might help. What are the stresses? In thick-walled cylinders. I want the longitudinal stress. That's fine. We found it. Wait. We found it. It took me a long time. It's very similar to something else that I thought it was gonna be. What the? There we go. Oh my god, chat. We found it. Look at this. Oh yeah, Sigma Z. Let's go. Oh, thank god. Okay. Wait, you can't even see it. Here it is, in all its glory. Okay, so now we can set this up, and we can figure out what our length is gonna be then. Sorry, I'm just imagining this being like the longest just like tube of mice. It's like a 5-inch radius, so it's 10 inches, so it's like the size of a plate. I don't know if you could fit that many mice in there, actually. I'm kind of thinking about it like with my hands. Like, I feel like you couldn't fit 9 mice in there. That's a lot of mice. We might have underestimated the nominal width of a mouse. It's fine. They're fine. It feels like a mouse is bigger than that. But I mean, we said they were 1.75 inches, which is like, okay, now that I think about it, maybe a mouse is yeah. Kind of like 11 mice. Oh wait, the 5.75 was only for 4 mice. What am I talking about? Okay, the other radius is much bigger. Never mind, that makes more sense. I was like, there's no way you're getting 9 mice in like less than a foot. It's not happening. Not unless you're stacking them on top of each other. Anyway, okay, let's set up the Sigma Z then. Which is kind of nice because we don't have to do anything. I guess we're just gonna... Wait a second, but I want to figure out the length. Wait, what the heck is happening? Oh shoot, uh-oh. That's not the right Sigma Z. Wait, what about the what? It's not the, sorry, maybe it isn't the longitudinal stress. It should be though, but shouldn't it depend on length? Or do we not gaff? The axial stress can be found separately. Cylinder has closed ends. Maybe we don't gaff about length, but I thought there was a sigma L. Why did I write coughs and dies in my notes? I don't know what that is. Oh, because I was yeah, never mind. I was coughing. I was like having a coughing fit in the middle of class. It's like, what was I talking about? Okay, why is there nothing based on the length? Shouldn't there be something based off of the length? Do I have to model it like a beam? No, I shouldn't have to do that. Where's L? I feel like there's an L in some of these equations, and I'm just like not looking at it. What the heck? Wait, is there L in any of these equations? Okay, well that's a syllabus. That's not what I need to look at. Modules. One of his had an L in it. Let me see if I can find it. Or maybe it didn't, and I'm just... God, also, you're reminding me I have an EE exam tomorrow. Not a midterm, it's just a quiz, but like, it's so... Guys, EE is really hard. Sigma L is Ri squared Pi. But where is Sigma L? Where are you? Sigma L. Oh, okay, okay, that's so weird. So it doesn't depend on the length at all. Wait, then we don't care. Wait, maybe we do care. Okay, we can care a little bit. I don't think it's gonna change anything. I think it's gonna give us a value that's like smaller. But we're gonna just say sigma L. Oh, sorry. Go back over here. This equals Pi Ri squared Pi times Ri squared minus Po times Ro squared over Ro squared minus Ri squared. I guess we can just maybe choose the amount of rows in our plane then. Doing simple nodal stuff for now. Didn't even get to capacitors yet. It's okay, I struggle with even regular node voltage analysis, so, you know. Well, I guess it's kind of funny because I'm just like doing a circuit, like we're doing transistors right now. And one of the things about a transistor is it's complicated, but there's a part where if you want to use a transistor as an amplifier to make your voice larger or a signal larger, you want to use like a capacitor sometimes to separate your AC source from your DC source, because your AC will be what you're amplifying and your DC will be your power. And you don't want your AC circuit affected by your DC circuit. And sometimes you can have like a resistor in there. And I was just trying to do like node voltage analysis, like to figure out what the voltage was at the node, and I was like, this is hard. I do not remember how to do this very well. Oh, whoops, I didn't do this. Wait, let me just do this. I don't know why I'm like subjecting this to a different place. There we go. And SL. Sigma L. RO, and then we just have another one of these for sigma RO3. I'm hoping that this comes out to be smaller, because then I don't have to choose a different mouse airplane. Okay, it's about the same. Let's see, 2763, 2728. Oh yeah! I don't really know what any of that means, but thanks. It's okay. I believe in you. It, Okay, 8 inch, okay, 8 inch, so it's kind of closer to like... I guess like 18 inches. It's like 8.75, so that makes sense. And then I'll just do the, I guess I kind of just should delete those other screenshots. I'll move this one. Wait, let me cook. Go back over here. And then we can do some dynamics real quick, or some Thormo. Learn linear algebra just because oh my god, yeah. Obviously. Or not, I shouldn't say obviously. But like, please learn linear algebra. It'll make your life so much easier. I can get rid of this. We don't need this. This is bad. I'm glad that I did not try and solve that by hand any more than that, because that would have been really bad. But now we have to figure out how long. It doesn't really matter, I guess, how long it is, but that feels strange to me. So, here we go. This is our mouse airplane. Whoops. I kind of want to hide these. Can I just clear? And clear. I kind of cleared it. Gave me some more space. So that's mouse airplane 1. Matrices are flipping lifesavers. Yeah, I know, and usually they let you have a calculator too, so you can row reduce on your calculator if you haven't figured that out already. For exams. And then I'm gonna do 2 seats, 1 aisle. Damn it, I didn't. Oh. Interesting. Okay. This is awesome. I'm having way too much fun with this. Or I'm having the right amount of fun. So this is... Wait. Let me put these there. Okay. So this is 4 mice. And then 0.002 or 9 mice for 0.003, and I'm gonna choose this one. So thickness is 0. I'm supposed to comment on the design process? I don't know, would it calculate the average, maximum, and tangential? The rough. Well, see, I kind of did it like backwards because I think they just needed you to like pick a thickness and then see like if it would fail, but I like found what the thickness should be to make it not fail with a safety factor. So we went above and beyond, chat. We designed the best flippin' mouse airplane we could. It can be scaled. I don't know, normally I feel like airplanes like this would have like at least 20 rows. It's cool, I'm just learning simple quadratics, so a matrix on a calculator won't be a problem for me. I can't tell if that means that like you're not allowed to use it, or like you are actually gonna be able to use it. You like this little mouse I drew, by the way? This is an awesome mouse. I like this guy a lot. He's reading a book on this awesome airplane we designed. Guys, I'm just happy. That was fun. That was really fun. See, if my classes were like that, I wouldn't be so bored all the time. Okay. So now we have to do boring stuff, unfortunately. I'm really glad I learned how to do the solver in MATLAB. That's actually super useful. And we didn't even need to do adiabatic compression in the atmosphere. Holy moly, that would have been frustrating. Okay, so I could either do thermo or I could do dynamics, and I kind of want to do dynamics. I do need to end a little early today because I started late, unfortunately. Unfortunately. Going to dynamics with the stream title Mouse Airplane is maybe not the right accurate Oh guys, I'm happy about our mouse. I think that's awesome. Oh wait, maybe I already have the problem. Did I paste it? I don't know, I said it like that. Oh, I did, okay. We can do some dynamics. Learning algebra 2 at school, so I don't have to worry about pre-calc stuff for school. Oh, okay, I see. No, what I mean is like if your EE class, like for example, some people, or like a fair amount of people didn't take linear algebra, or for us it's linear analysis as MEs, before they took their EE class. And you know, when we would have EE exams, they would be like, okay, you can like use a graphing calculator or whatever. And they'd just be like, do Kramer's rule for your 4x4 node voltage analysis. Like 4 unknowns and stuff. And people were just doing that. And I was like, you know, you can just like put it into a matrix and then like have it solve it for you, right? And people were like, what? There's somebody who I told that this year as a 3rd year, and they were like, I didn't know that. I'm like, how have you been, how have you not been getting so mad? I would get so mad instantly if I had to do all that by hand. Jeez. I think some people have more patience than I do. I also am not very good at I know my strengths and weaknesses, and I know that I definitely make some calculation errors, so I tend to not like doing that. Alright. Oh, we get to choose a rotating frame. Okay. So, at a given moment, arm OC rotates with constant angular velocity, n equals 5, while disk AB rotates with constant angular velocity, p. Find appropriate rotating frame and origin, and use this frame to find the velocity and acceleration of point A. Let's do the easy one. So we have a couple choices for rotating origins, but we're gonna choose... So the main thing is, do we want to use 1 omega or 2 omegas? And then we kind of put our origin where we want to. So I'm going to choose 2 omegas. We're going to do a combined rotating system. So this is going to be n plus p. And our origin has to be at a spot that is affected by both those rotations. So we're going to choose B. And they already chose that, actually, where they are. So that works for us. This is going to make our lives just a lot easier. We'll have an omega dot, but we won't have really alpha dots and stuff like that, or R dots. So, but we'll start with the easy one. So VA. I have to write some givens. I forgot about that. My bad. Given. The given is going to be n equals 5 radians per second, and let's see, that's going around in the negative y direction. I'm pausing because I don't know if I need to... No, it's still going in the negative y direction, so it's not an issue, even though it's in this frame. Yeah, calculators are so much more effective than people think they are, including complex numbers and solutions to polynomial equations. Yeah, exactly. And I really encourage people to check their work with solvers and with calculators, because some people are... I think there's a difference between, you know, getting to a place where you need to solve, like, let's say you're learning about quadratics. Obviously, solving quadratics by hand is really useful because you kind of need to work with them. But if you're not working on it, let's say you're doing dynamics or something, there are a lot of quadratics and dynamics because of the way that stuff is related, variables are related. You don't need to solve that by hand, so you can just do that with a solver. And, like, I don't know if I have an example of it. I do. This is part of the work for my lab for this class. This is not useful for me to do by hand, all of these cross products and all of these things, which then I have to plug the cross products into. This is me. So it's like, you know, I think I asked our instructor, he was like, yeah, please don't do that by hand, please use a solver unless you really want to do it by hand, and then, like, don't. Just don't. VA, right? VA? Yeah. AA. Okay, so VA is going to equal V of the origin, which is a velocity that we actually is going to have a velocity. Is that right? Let me wait a second. Let me check that. I think it's VA plus then VO, but let me see. No, I think she did say that. I think it's just that we did the acceleration out like this. This is a lot easier to do with accelerations. Sorry. This makes your acceleration much, much easier to do. So I would suggest doing it this way. Because I'm not gonna lie, I don't want to have to do an internal rotating frame to my already rotating frame. Like, why don't we just do one rotating frame? For example, in calculating the trajectory, the equation is a quadratic, so you use a quadratic formula. Exactly, yeah, the equation for time. Yeah, a lot of the times you won't have to do that, because the problems where they'll ask you for time, your initial velocity will be 0, and then you won't have to solve a quadratic, you'll just solve, like, you'll solve Sorry, I'm just trying to find if we actually did this velocity. I think we did. New frame. Why did I not write down what our velocity was? Did I not write it down? That's fun. I guess I just didn't write it down. That's awesome. Great job, me. It'll just be a squared relationship. It won't be like a quadratic, but yeah, you're completely right. It would just be quadratic formula. Also, I don't know, quadratic formula is so powerful. People are like, oh man, I can't solve this thing, I can't factor, whatever. I'm like, quadratic formula be upon you. Don't worry about it. Don't even try. Omega cross R A with respect to B, so that's our origin, plus R dot X A X Y Z. I'm trying to say A, just in case we have other particles. I don't know if it'll happen, but it kind of helps me out. Alright, so VB. VB, it does exist. I want to say that that is just, well, I know what it is. It's omega, or I guess it's N, crossed with RB with respect to O. And then called a, wait, let's see. For systems of equations, is pre-calc, linear algebra serve any other purpose? Oh, except systems. Yes, linear algebra is everything. I don't know how to explain it other than that. All of algebra is just projections of linear algebra. And yeah, linear algebra is the way that we can use linear algebra is it's kind of like a different world. So the way that I kind of think about it is like you have your hub world, which is like, you know, you're doing all your like algebra, like you're like, oh my gosh, numbers exist, that's awesome, wow, yay, it's so cool. And like you could just probably go through life and not need anything like other than this. But then you like see calculus and you're like, whoa, like this is about like relationships between stuff and how we can like model our world in cool ways, and you absolutely need this like if you're gonna go to any sort of physical science, whether it's like chemistry or it's, you know, physics or it's anything like that, like stuff is changing, right? So we need to study that. It's the study of change kind of. And then you have like linear algebra, which really is like a math thing, but it's also everything, because everything is math, right? When you're using math. And so one of the big things about linear algebra is being able to transform things. It's like, let's say you have a vector and it lives in one place, right? We define it in a certain coordinate system, a vector. Let's just say it's like 1, 0, 0. And we want to change our coordinate system to be like this, which happens a lot in physical sciences. Like, for example, in this problem, right? Let's say we have this vector here in this global coordinate system, it might be moving like this. But if we want to change it and our coordinate system is over here, we want to define that same vector in that coordinate system. Linear algebra gives us a way, among many other things, to transform any vector to a different space. That's one thing it does. Another thing it does is let us, for any transformation, so like if you want to rotate something, that's a transformation. If you want to scale something, that's a transformation. If you want to basically do anything to any vector, that is a transformation. And every system of equations is actually a transformation that's going on, right? You put in something and you get out a solution, right? That's a transformation. So it allows us to analyze that, and it allows us to manipulate that, and none of that is calculus, actually. So I really think that people could learn linear before they learn calculus, and it would be helpful more. So I think, because at least as an engineer, the one thing that pisses me off the most, I think it might be the single most thing that is like the most annoying thing consistently over every single professor I've had about math is the way that people understand vectors, or the way that people treat vectors as an engineer is infuriating to me. Like with what I'm doing right now, right? Like let's say I'm going to go and I'm going to say like, okay, omega cross RA with respect to B plus RA. Oh, and let's define this. R hat is going to be 0. Because when we take away the motion, there's no... A is not moving inward or anything at a velocity. Or I can just cross it out. Like, let's say, even just this is not what people do. This is... People write things like this as an engineer. And I'm like, I don't even know how to begin with, like, this being the sole way every single professor writes it. And not even just because I'm like dyslexic or something, and it's really hard for me to read vectors written like that, which is that's one of the reasons why I write them like this, because I can actually read them and not fuck them up like every time. But like when you're writing a cross product, you write the cross product in this form and you put the vectors in there. That is, you know, it's not an issue. Anyway, what do you mean by transformation? So a transformation is basically you're just turning something into something else, and there's some rule, right? So maybe your transformation is like, we have a vector here, and then you're going to turn it into a vector here. Now this transformation could be a lot of different things. We could be rotating that vector, simply, right? That could be an example. We could also be scaling the vector in these directions. We could be adding another vector to this vector to get that vector. So really you can do a lot of different things. It's kind of just like just how we can write any equation, basically, right? Like maybe this is like 3x plus 4y equals a, where x and y are your inputs and a is your output. And then when you start to do more of this, then it becomes like, okay, well then you have, let's say 4x plus 6y equals b. And if we're in 2D, that's all we get. But if we start to think about this, okay, so this is a system of equations that we've just made up, right? These are two equations that define something, and this vector is at, like, let's say this vector is at a and b, and this vector is at x and y. Then if we were to write this into a matrix, we say, okay, 3, 4, 4, 6 is our matrix of coefficients. And if we multiply that by x and y, then we get AB. And the reason why I say if you multiply it by x and y is because if we look at this, if we multiply this matrix here, we get 3x plus 4y equals A, right? So by setting up this transformation, every single matrix you can write is actually a transformation, and every single system of equations you write is also a transformation. It's just transforming it in space in a certain way. I guess it'll be more useful when I learn what vectors are. Oh, well, vectors are basically just, if you have a point, right, so you know what a point is. A point has two coordinates. Let's say like this point is 1, 1. All a vector is we go from the origin and we point to that point. That's all that a vector is. And so vectors have two properties. They have a magnitude, which is how big they are. So this guy is a length, right? He has some length. And then they have a direction, right? So there's an angle that we can say that this vector has. And you can think about it like that. You can think about like how much up are we going and how far? Or you can also just think about it, well, okay, we have this point and the vector is pointing to that point. And then it becomes a lot of, you can see where like trigonometry starts to come into play, right? So if we want to say like, how long is this vector? And maybe we know this vector has length equals 2 or something, which it wouldn't have this point anymore if it was length equals 2. And we say like, okay, we know that it's at 45 degrees. Then if we want to figure out what point it goes to, we say the vector goes to L cosine 45, L sine 45. And that's how we define that vector, and that's what this point would be. That's really all the vectors are. It's just pointing to a point. And the way that we define it is just a little bit interesting. And the cool thing about vectors is they're literally everywhere. So velocity is a vector, right? How fast something is going. We want to know how fast it's going. 45 miles per hour. And in what direction is that speed? This is the speed, and then the velocity is the direction also. Gravity vector, right, points down towards the Earth. Gravitational field. What other vectors do we have? We have... You can pretty much write anything as a vector if you want. I mean, but like... Oh, polar coordinates. Yeah, and polar coordinates. You can use polar coordinates in conjunction with vectors sometimes, like certain functions in, you know, maybe you're trying to analyze, and this is complicated, this is not something that you'd be doing, but maybe you're trying to analyze a system where you have like a ball on a string or something, right? And you're trying to figure out what that velocity of that ball looks like. You might want to define it in polar coordinates, because then it's like, okay, well, if this velocity is up here. Another thing about vectors is you can kind of move vectors around. Like this velocity, I can draw it here. It doesn't really matter where that origin is, it just matters what the magnitude and direction is, and the magnitude and the direction are the same. But in this case, right, it is kind of like on the ball, so it's on the ball. What else? You can also add vectors, so maybe you're on a train, and the train's moving. You're standing on the train's going this way, and you're running in this direction. The way that you'd find your speed is by saying the train's speed, so v train, plus vu equals your actual velocity. Because you're going faster, and you're adding the train. So yeah, there's a lot of cool things with vectors. Everything's kind of a vector, if you think about it. Also, all numbers are vectors. My Wi-Fi sucks, I might be missing some of the stuff. Oh, I'm sorry about that. It might be my bitrate also, I'm not gonna lie. Alright, I'm just gonna set this up, and then I do have to get ready to go to class. Lol. God, guys, this class that I have to go to is so bored. You save me, chat, please. Sorry. It's so over. I wish I could mouse airplane more instead of going to this class. IJK. I don't even like that I have to do that, but that's just how we do cross products. I don't like writing any I's or J's. And then R. Oh, RB with respect to O. So, RB with respect to O? Oh. Yeah. Alright, we're going... Negative X. 0.18. I'm just converting it to meters. And then we go up in the Z. So 0y. And then we go up in the Z, which is 0.1. And so in this example, like this is our coordinate system right here. We're trying to make this vector that points from B to O. So all we have to do is say, okay, so how much up are we going? Well, we're going 100 millimeters up. So that's what our Z coordinate of our vector is. And then how much over are we going? Well, we're going in the negative X direction, and we're going 180 millimeters, so that's our vector. So then we would write that like X direction, Y direction, Z direction. I believe you'll survive class. I will, it's okay, I have a friend in it, and we just have immense hater energy the entire time. I felt so bad for her because her file kept getting corrupted, and it wouldn't stop corrupting, it just kept corrupting. It was so painful. I was like, oh my god, can it just stop corrupting, please? Because she couldn't do, like, any of the modeling stuff. I just realized I was supposed to make an I-beam. Nah, it's fine. I think he probably is gonna give it, or I can steal someone else's. Not steal. Borrow one from my friend. Where's the... Oh, 100 millimeters. Let's say. I think the radius matters. 100 millimeters, so that's in the X direction, so 0.1. And then we just have these cross products. That's another thing linear algebra is good for, although you probably learn cross products before you take linear. But, yeah, it is also good for those. Why would I do that one? Oh, I would do that one. So, it's negative, positive. So, 5 times the 0.1. Wait, positive, negative. Oh wait, that's positive. God damn it. Negative. In cross products, positive, negative, positive, but you do that there, so the middle one is also positive. Don't worry about it. That's really not super important. And then plus, minus, so that one will be, oh god, minus triple negative, which is a negative. Okay, I really need to go after I do this last cross product. That's a positive. So 25 minus plus. I hope that's right. I guess we can just kind of look at it if it's 2.5. Yeah, it's probably right. The J component's right. Alright. Okay, chat. Thanks for hanging out. We made a great mouse airplane. I'm so happy about this mouse airplane. You don't even... Oh my god. I'm gonna show this mouse airplane off to everybody. I'm gonna be like, guys, please look at my mouse airplane. Please, you don't understand. My 9-seat across mouse airplane. We really did it today. It was a breakthrough. I'm really happy. Alright. I will be back on Saturday, actually. Change of stream date. Normally we do Sundays, but Damie, what's up? I don't know what cross products are. I learned simple matrices just for EE. I won't lie, but I might as well finish the course sometime. Cross products are kind of confusing. They're a little weird. They're very much a mathematical thing that has a lot of practical applications, but if you just learn what a cross product is without having that application, you're gonna be like, okay, cool, so like why do we care? Probably. But it is cool. It basically means if you take two vectors, you're trying to find a vector that's perpendicular to both of those vectors. So if you have like, if you can imagine like a 90-degree angle, then if you take the cross product, your vector is gonna come out at the other angle. It kind of like makes a coordinate system, if you think about it like that. And then there's a bunch of right-hand rule stuff where you have to do like gang signs, which that's a lot of like, you do that, generally you do it for like electromagnetics. Had fun? Oh, thanks, I'm glad you had fun. Good luck with your EE. I'm wishing you all of the best in all of your calculations. I hope you get no bad numbers. Hope everybody gets no bad numbers. I am gonna go to class. I'll see you guys on Saturday. We're probably gonna be doing dynamic.